Okay, thank you very much for the introduction. So, awesome talk. That's quite big footsteps to step into right now. So I hope I won't bore you to death with what I'm talking about now. What I will be talking about now is use-before-initialization attacks on the Linux kernel. And I assume that most of you haven't heard anything about use-before-initialization vulnerabilities, at least up until yesterday, where there was the safe-init talk, which was exactly targeting the same thing with a defense mechanism. So what you did probably hear about, though, were use-after-free attacks, which are very related. They share some very specific characteristics. In particular, if you have such a use-after-free vulnerability, you have a pointer which targets a specific part of the heap. And the vulnerability comes in that first the pointer, or rather the stack, the heap object is freed, and afterwards the pointer is dereferenced for usage. What happens here effectively is that there is no guarantee what the dereference will actually do. In most benign cases, you just hope that the heap hasn't written something else over the object there, and everything works out fine. However, if there is some interleaving execution, there might be some malicious stuff going on. For example, you can just allocate an object which overlaps the same memory region, and suddenly dereferencing that foo pointer will lead to something bad. For example, malicious execution or something similar. Now, what does this have to do with uninitialized use of variables? The setup is different. This time we are on the stack, and we have some struct pointer foo, which is defined, but it's not initialized. However, afterwards it's still dereferenced. The same thing is going on here as with use-after-free. You still target a specific part of the memory where you have no guarantee what's in it. What's usually in it is something that was left over from a previous execution. So if you have some way to call a function which uses the same memory, you can do some malicious stuff with that. You can just fill up the stack first with some kind of setup function, which can contain a lot of bad stuff, for example, malicious addresses. Then dereferencing that foo pointer in the vulnerable function after the initial function has finished and the frame was deallocated, will use the evil leftover data, deallocate it and execute. And that's basically the same thing happening now as in use-after-free, except the setup is a little bit different. To summarize, if you want to exploit an uninitialized use of a variable, what you need is some overlapping memory for both a setup function, which writes malicious data, and a vulnerable function, which does uninitialized usage of a variable. If you achieve this, then you can have arbitrary read, write, or execution going on. So now this seems rather simple for now, so why actually do this talk? Why talk about such an attack when it's so related to stuff we already know? Well, in reality, nobody really thinks of uninitialized use problems as a security vulnerability. They're completely overlooked. If you look at the kernel patches for Linux kernel in the last 2 years, you have like 16 different patches which target uninitialized usage, and only a single one of them has actually been reported as a CVE. Since there's only one CVE, most of the memory safety techniques also tend to overlook this stuff, and they don't target it at all. Overall, there is this widespread belief among programmers that uninitialized memory seems to be uncontrollable, so the value that's there is effectively random. So it's maybe a bug, but it's not a security critical bug. A lot of this stems from the fact that manually exploiting these uninitialized users is pretty hard, especially if you consider something like the Linux kernel stack, as we are doing. So just consider the setup as explained before. We need to have some overlapping memory between a setup function which writes malicious data in the exit memory location where the vulnerable function will have an uninitialized use. What does this mean for the Linux kernel? Well, assume that there is already a vulnerable function given, so all the hard work of finding the vulnerability is already done for you. Then just exploiting it takes a lot of more work as well, because you need to select some way to write this data. Writing on the kernel stack mostly means that you need to have some way to go from user data to kernel data. and that's mostly done with a syscall. And you have, in most systems, 300 different syscalls. So which one do you take? Which one overlaps the memory you need? And that's only the first layer, because there's also a second layer where you have now different parameters and different values for each of these syscalls. So finding the correct one is really hard. So doing this manually, a lot of work. Now our question was, can you automate this process, and how well can you do? The primary question of this is, of course, we need overlapping memory. So the first question we want to answer is, where do syscalls actually overlap? And when we figured out that 90% of all system calls only actually use the first 2 kilobytes of the kernel stack. So if we want to achieve overlapping memory between two syscalls, then this is the most interesting region for us to target. However, it's also a really hard region to target, since a lot of syscalls allocate memory there for their data and they initialize memory correctly. A lot of stuff might be overwritten in between two syscalls. So we need some deterministic way of getting the data there with as high a certainty as possible. However, the remainder of the stack is, of course, still interesting. So we developed 2 different complementary attack techniques. One we call deterministic stack spraying, which specifically targets the first 2 kilobytes, and exhaustive memory spraying, which targets the whole stack, but is mostly used for the remaining parts, so the remaining 6 or 14 kilobytes. Now, since the talk is only 15 minutes long, I can't go into detail on both of them, so I'll select the most interesting one, which is the deterministic stack spraying, but I highly urge you, of course, to read our paper for more explanation on the second one. So deterministic stack spraying has 2 components. The first goal we have is to find a syscall with fitting parameters to achieve some memory control. That means, first, we want to know what is the syscall and what are the parameters. For this, we use symbolic execution to explore all possible execution paths of the syscalls. The return from symbolic execution in this case is simply a set of constraints, where one set of constraints uniquely determines one execution path. This means that we can basically select the parameters for each syscall to run at least once for each execution path. And using this, we then do some dynamic verification. We run the syscall and check, after return of the syscall, which parts of the stack are actually under our control. So how does this look in detail? For symbolic execution, assume we have some syscall which takes some integer parameters and some buffer. The function itself is rather simple, so we have 3 possible execution paths. What symbolic execution does now is each time a junction is reached, so where the code execution can split in 2 paths, it will determine what the constraints are for each individual execution path. For example, on the first if, we can have P1 is smaller than 5, and then the opposing execution would be P1 is bigger or equal 5. Doing this for all the if then else cases leaves us with all the execution paths. Now, after I said this, everyone who has done symbolic execution also knows that symbolic execution does have a lot of problem if there's some loop in there which has some bound which is symbolic. So in our case, all the symbolic stuff should be a parameter. Well, in this particular case, there are 2 things which are important. First, it needs to be handled, because if there is a loop which is unbounded, then we would have 1 path for each additional execution of the loop. Since we don't actually know when the variable is bounded, this is a lot. This is just path explosion, not handled in any way. What symbolic execution would usually do is to use some kind of heuristic to select the most likely path or something else. However, for us, this is not enough. Because if we have a loop, there could be a loop which is really useful for us. For example, a loop which just continually writes data from a buffer onto the stack. Any type of heuristic for symbolic execution wouldn't really work here. So what we're doing is we just take note that a loop exists in a particular part, and then we will use a fuzzer to selectively execute this loop in multiple ways by fuzzing the loop variable that corresponds to this loop condition. So after we have found all of the constraints and we've found all of the loops that we need to fuzz, we are left with a number of execution paths which we need to execute and the constraints which identify this path. So we solve those constraints, get some specific parameter input, and for all of the parameters which are not symbolic, so which are not used to determine control flow, we just add some magic values into them that we can then see if they are left on the stack somewhere. The assumption here is, of course, that stuff that is not used for control flow is probably some kind of data that is transferred from user space to kernel space. We do this for all of the execution paths, and we end up with a number of imprints that show for the stack which sections of the stack can be controlled by one particular path of execution. Using these imprints, summing them together gives us another look at what the stack actually looks like. So on the one hand, we can say for one syscall, we control this region of the memory, but the reverse is also true. If we are interested in what kind of syscalls are able to control one memory region, we can also figure this out. In particular, this does not exactly have to be uniquely determined, which means that multiple syscalls can control the same region of memory. So what we've achieved here is now we basically solved the problem that we had in the beginning. We have a vulnerable function, and now we also have a way to determine what the setup should look like to exploit this particular vulnerable function. We use our tool, we use our deterministic stack spraying technique to automatically derive a syscall which fits in exactly this memory location and write some malicious data there. Good, so this is how the exploit looks like. Now, our question is, again, how well do we actually do? And measuring this is pretty interesting. So what we did first is check how much of the kernel can we actually control. And the results, at least for me, are pretty satisfying. For the first 2 kilobytes of the stack, so where most of the data resides and most of the data should actually also be overwritten, we control 39% of the stack. So quite a bit more than 1/3 is completely under attacker control. Now, if we combine deterministic stack spraying and exhaustive memory spraying, then for the whole stack, we control 91%. So the vast majority overall. Besides the coverage, we also want to know how would this look like in a real exploit, because there have been a few, like 2 or 3 exploits which actually did this with a lot of manual labor. For example, by Case Cook in 2010, there was an exploit which used an uninitialized pointer for a write and basically achieved privilege escalation in the Linux kernel. It was a pretty big deal at that time. The basic setup that he used was a setup function which was part of a device-specific syscall, which used a vulnerability in another device-specific syscall. So they were pretty closely related. He only found that one link. When we used our tool on this, we found 27 syscalls overall that pretty much achieved the exact same thing. So we have 27 different types of syscalls we can use to exploit the vulnerability that he found. And I assume with our tool, we probably did, time-wise at least, much better. It took something like a day to compute all of these examples. Okay, so when you do an attack, you also need to tell people how to defend against it. That's kind of the point, I guess. The Safe Init paper does this in great detail, and it does it very well. So I'll only briefly talk about this as a general thing. The problem, of course, is that there are pointer-type fields which are uninitialized. So you figure out what these unsafe pointer-type fields are. Usually, there are one of 2 cases. The first one is where you immediately just use or dereference the pointer after it has been defined but not initialized. And the second one, where you just can't prove anything conclusively, is when the struct or the pointer is defined but then immediately passed to another function. In both of these cases, proving anything that it is initialized at some point is pretty hard, so pretty difficult. We can't really do anything about that, so what do? We initialize it with 0, because not today at least, this is a safe way to do this. A few years ago, this would have been a pretty bad idea, but luckily, of course, Linux kernel takes care of null pointer dereferences by now. So 0 initializing is pretty good. Should be said that, again, safe init is basically does more, so we are basically just a clear subset of the safe init approach with our mitigation mechanism. The performance overhead is relatively small, so only checking the syscalls themselves, we average a 2% performance overhead, and checking actual user space programs with the spec benchmark is something like 0.5%. Okay, so since my time is up, some short conclusions. So I hope that uninitialized stack variables will in the future be considered a security vulnerability, because controlling 91% of the stack is pretty damning if you have a lot of vulnerabilities left in the kernel and in other software as well. So, and I also hope that memory safety techniques in the future should consider this as a prevention target. And yeah, with these takeaway points, I'm basically done. Thank you very much for the attention.